Okay, so we're continuing on functions of several variables, and we're going to look briefly at limits and continuity. So these are limits of functions of two variables. Okay, and you can generalize to functions of n variables. And we're not going to linger here, okay, so we're going to just mention this briefly before we move on to more interesting things of partial differentiation and so on. Okay, so you studied limits in a function of one variable with Kathy. And you said that some function of x had a limit L, okay, as x went to some value a, okay? And in other words, you said that L is the limit of f of x as x goes to a, okay, if for all epsilon greater than 0, there exists a delta less than 0, such that the distance x minus a is less than delta implies that f of x minus this limit L is less than epsilon. Okay, so it's a rather complicated statement, but all it says is that if we draw the graph of f of x, okay, and we want the limit as x goes to a, sorry, should be an arrow there. Okay, so this is the point A. Then you look at the distance from A and it should be less than delta. Okay, so let's have an A plus delta and an A minus delta. Okay, you're taking the modulus here, so you can be either plus or minus delta from A. So as long as you choose an x in this region, okay, so you're choosing an x, let's say here, choose this x, it's less than delta. This implies that your function at that x, this value of your function minus L should be less than some epsilon. Okay, so if the function doesn't vary much in this region, so this is the extremes, okay, if the function stays within epsilon of L, then you've got a limit, okay, this L. Okay, so we can generalize this and think about a function of two variables. So let's define the limit of a function of two variables. So L is the limit of a function of two variables, f of x and y, if, oh yes, at x equals a, y equals b, if there exists, sorry, if for an epsilon, for all epsilon greater than 0, there exists a delta which is greater than 0, such that, and now it's not the distance in one dimension, we have to think about two dimensions. Let's draw an x, y, z. Okay, so we choose values of x and y and then we get some function. So let's draw the function. Okay, let's pretend it's some sheet. Okay, so this is some sheet. Okay, with some positive values of z. Okay, and each point in the sheet is the value of the function f of x and y for some x, y coordinate. Okay, so we're going to take the limit at x equals a, y equals b. So let's take this point to be a, b. Okay, and here, just like you wanted to be within delta of A, we still want to be within delta. Okay, but in this case, it's a disk. Okay, a disk of radius delta. Okay, so let me continue with this. We want the distance of A and B from X and Y. So the distance between X, Y, and A and B is X minus A squared plus Y minus B squared, all square root. Okay, and we want this to be less than delta. Okay, and this should imply that your function xy minus L is less than epsilon. Okay, so this is what we need for our limit to exist. Okay, so what this is saying is that if you choose an x and y, the distance between that point and A and B should be less than delta. Okay, so if this is a disk of radius delta, then x and y should be within this disk. Okay, and for those x, y, A, and b's, this should happen. Your function, the value of the function, so the point on this sheet, take away L should be less than epsilon. Okay, so all the values of the points on the sheet corresponding to this disk, so maybe it's this region, okay, this region of the sheet, the values should all satisfy this. Okay, now because it's just the distance that matters, okay, it shouldn't depend on how you approach AB. Okay, so you could start from here and approach AB in this direction, or you could approach AB in this direction or in this direction. Okay, and if the limit exists, then it won't matter what direction you choose. Okay, so how you vary x and y to get to A and B. Yes, so we write this as the limit x goes to A, y goes to B of our function f of xy. Okay. Okay, and this is not the same. Okay, it's important to note it's not the same as taking two limits kind of consecutively. So it's not the same as the limit of y goes to b of the limit of x goes to a, f of x, y. Nor if you swap x and y, so the limit of x to a, the limit of y to b, of f of x and y. Okay, so these things may exist. These may exist when this one, let's call this star, when star doesn't. Okay, and if you get different values, okay, so this is basically going different ways, taking different paths. Okay, either go along the x-axis or the y-axis, etc. If you take different paths and you get a different result, then this limit won't exist. So we can have a look at an example. Let me clean up the board a little. Okay, so let's think of an example. Let's think of the function f of x, y equals x squared minus y squared over x squared plus y squared. Okay, and let's take the limit at x equals 0, y equals 0. Okay, so this function is defined everywhere in R2. Okay, so x and y can take any value, except it's not defined at the origin. Okay, and that's where we're going to want to take the limit. Okay, so our function doesn't necessarily have to exist at the value of a, b. Okay, so we never actually jump into the value, the point a, b. Okay, we just approach it. Okay, so let's think about the limit, so this top line, the limit y to 0, because we're thinking about 0, 0. But first we take the limit of x to 0, and our function is this x squared minus y squared over x squared plus y squared. Okay, so let's take the limit x to 0 first. Okay, and leave the limit y to 0 untouched. So if we take the limit of x to 0, this becomes minus y squared over y squared. Okay, which is the limit y to 0 of minus 1. Okay, which is just minus 1. Okay, and now let's think about the limit taken the other way around. So we do the limit of x to 0 last, after we do the limit y to 0 of the function x squared minus y squared over x squared plus y squared. Okay, so this equals the limit of x to 0. And now we're putting y equals 0. So this becomes x squared over x squared, which is the limit x to 0 of plus 1. Okay, so these two things give different results, but they give a result. So this thing exists, this thing exists. Okay, but because they give different results, it means this doesn't exist. Okay, implies that the limit of x, y to 0, 0 of this function x squared minus y squared over x squared plus y squared doesn't exist. Okay, so it's much easier to show that limits don't exist than actually calculate the value of a limit. Okay, so what does this mean kind of geometrically? Well, if we think about our xy plane, here we want the limit at 0, 0, so at the origin. Okay, and what we're saying is that it shouldn't matter how we move. So this is our point AB. Okay, and we have a general point x, y. Okay, and it shouldn't matter for this limit to exist, the true two variable limit, it shouldn't matter how we move this point xy towards AB. Okay, if we move it in this direction, or in this direction, or around like this, okay, or like this, it shouldn't matter. Okay, we should get the same result, and it should be L. Okay. In this case, the first one, we take the limit of x to 0 first. Now the limit x to 0 means we're coming along the y-axis. So we first say limit of x to 0. That means we're placed on the y-axis, and then we go y to 0. So we're coming in this direction along the y-axis, okay, either down or up. And if we come in this direction, then we find our limit is minus 1. Okay, so if we come along the y-axis, we get minus 1. Okay, if we do the opposite, or the other version, we first set y to 0. That means we're coming along the x-axis. Okay, either from positive x or negative x. If we do that, so we set y to 0 first, that puts us on the x-axis, and now we take the limit x to 0, so we come in along the x-axis. Then we get, so if we come along the x-axis, we get plus 1. Okay, so here clearly it does depend, the value of the limit, the value of L, the value of the function, okay, effectively does depend on which direction you're coming. Okay, so to show if a limit doesn't exist, you just consider kind of two different paths. Okay, so you can do it like this and show that they're unequal, kind of not equal to each other. Okay, so the last thing I just want to mention is continuity. And a function is continuous at AB if, just write it here, okay, because it's in the notes. A function is continuous at AB if the limit of x, y to AB of your function equals a b. Okay, and if the function is continuous, then to find the limit you can just plug in the values a, b. Okay, so maybe what's the limit of x, y goes to 2, 1 of x squared times y? Well, you just plug in x equals 2, y equals 1. It's 2 squared times 1, 4. Okay. So if you've got a polynomial or some that's continuous, then you do just plug in the point a, b. Okay, if you've got a 0 on the bottom, or your function is indeterminate, when you take the limit, then you have to think a bit harder. Okay, but let's not linger. Let's move on to something more interesting. So partial differentiation is coming next.